Hi everyone, today we are talking about lesson 5.1, the beginning exploration of logarithms. Today's lesson is starting on page 59. Now on page 59, we see this little chart here that is dealing with the method of logarithms. And essentially what logarithms do is it helps us simplify some large or small numbers, basically kind of an involvement with exponentials. And we've used this a little bit before already. And basically what our calculator does is it stores a pattern. Because what we notice is if, for instance, I added 3 and 5, I would get 8. Well, if we look down here at these charts, if I multiply 1,000 plus 100 or times 100,000, I get 100 million. Or if I did 8 times 32, I get this 256. So what we see is this pattern. If I did another set, for instance, like 2 and 7 adds to be 9. Well, 100 times 10 million is 1 billion. 4 times 128 is 512. And our calculators have these patterns stored inside it using our logarithms, right? So that's what a logarithm is doing, is it is these patterns that are being stored. And again, if we skip ahead then to page 61, we see again the importance of this in that our logarithm is what we call the inverse of our exponentials, and they kind of help each other be solved oftentimes. So notice our log will always have the same base as the exponential that it is inverses with, right? So if it's a log with the base b, b would be the base of our exponential, and then of x equals y. So to convert between the forms, you always start with that base. And I like to call this swoop-de-swoop. It almost looks like a G for log. And so b to the y power equals x, right? So another example, if I had log of x, and then we have, let's say, 7 equals y. If I want to rewrite this then as an exponential, my base of my log is x, so the base of my exponential would be x to the y power equals 7. Okay, so just converting between those two forms. And again, the importance of these is that they share this inverse relationship. So if we take our calculators and we graph 10 to the x power and then log of x, if we zoom 6, we're going to notice that we have this inverse relationship. And again, another way we can tell that is that these are reflections of each other over that line y equals x. So we can see that happening here for part B. How do these work? Well, they are reflections over y equals x. And again, with that inverse relationship that we see happening in our graph as well, we can also take a look at some of the points. So for part C, it says the point 2, 0 or 2, 100 lies on 10 to the x because 10 squared is 100. Well, if we go under our table, we still have this in ask mode. If I graph x, again, I see that that 100 is its output. Well, if I look at 100, I see that on that other graph, I have that x output value of 2. So again, showing that flip-flopping nature on this. So we see if 2, 100 lies on y equals 10 to the x, then y equals 10 to the, then we have that other point, 100, 2, is going to lie on our other graph, y equals log of x. So again, this is what this is showing us, is that log of 100 equals 2. Now our domain for our log graph, if we look at this, if we go back to our graph here, our log graph's domain is that basically anything smaller than 0, including 0, is not going to work out. It's only going to be x values that are bigger than 0 are going to give us an output value. But officially for our range, it doesn't look like it initially, but it's actually going towards negative infinity. Like if we again looked at this graph here and we plugged in like 0.001, so we're really close to 0 but not quite there, we notice we have this output value of negative 3 for that graph. Or if we put in like 0.00001, even smaller number, we see it's getting more negative on that output value. So it is officially going to negative infinity. Now, a reminder, your domain and range then for an exponential is just the flip-flop, right? Whatever the domain was for our log graph is the range for our exponential, and we can kind of confirm that. If we look at this graph, notice we're going only from numbers above 0, not including 0, but up to positive infinity. And then our domain would be all real numbers, right? Negative infinity to positive infinity. Officially, we have an x output value for everything on that blue graph. So we just, again, flip-flop that. And again, the domain and the range are the vice versa of each other's. All right, now, again, connecting this back to the idea, if we look here, why is there a vertical asymptote at x equals 0? Well, the exponential form of our graph, right, y equals log base b of x is b to the y power equals x, right? We swoop it around. And then in a exponential, so in an exponential, b cannot equal 0. So thus, it's going to have a vertical asymptote at 0 in this logarithm graph. So we see that's why that's occurring on there. And we do notice again that this log graph is increasing at all times. So always increasing. And then as our x approaches infinity, again, we're noticing that the y's are increasing. Now, big part of today then is talking about our rules. Okay, we see this on the bottom of page 62, and we have some of the rules for our two most common logs that we see on our calculator, what we call the common log, all right, which is log base 10, and the natural log, which is log base e. So these are our two most common ones, and again, what these really are log base 10, and then this is log with a base of e each time. And if our x value is 1, so we take log of 1, what we're going to notice is that we end up with an output value of 0. Log of 10 is going to give us an output value of 1. Log of 10 squared gives us 2. And we can see kind of so on and so forth that this is 1, 2, this would be 5. And that's going to also work out with our ln's, right? ln of 0 is 1. Oops. Oh, I'm sorry. ln of 1 is 0. Excuse me, we have an error message otherwise. And then we have ln of e. Oops, not pi. E is going to be 1. And then ln of e squared. Oops, e squared. We see the 2. So again, that pattern is going to kind of hold through that these just cancel out. So again, log base 10 of 10, it's like they cancel to be 1. ln of e also kind of cancels out to be 1. And then when we kind of start talking about other forms besides those, okay, your log of any base of 1 is going to be 0. And that's because b to the 0 power is 1. Anytime your base of your log and this exponential match each other, they cancel out to be 1. And that's because anything to the first power is itself. These again kind of cancel out, and then we're left with that exponent, so it would equal x. and that's because b to the x equals b to the x. ln of 1 is 0, because e to the 0 power is 1. ln of e, again, kind of cancels out to get 1 on that. E to the first is e, and then e to the x. Well, it's ln of e cancels out. Okay, and again, that's going back to what we talked about up above here with those canceling out. Now, oftentimes, why do we need this? Okay, well, again, sometimes to evaluate, let's say you don't have a calculator, we can use the properties of exponentials to help us out. Because if I want to find the value of this log, if I rewrite this as an exponential, I actually have a better chance of solving this, right? 3 to the x power equals 27 would be the exponential form of this log. And I know that 3 to the third power equals 27. So my final answer here is that x is going to equal 3 because it's the third power. In my next example, again, if I want to evaluate this without a calculator, I have, if I rewrite this as an exponential, 4 to the x power equals 2. Well, really, on this one, we know that the 4 to the 1/2 power is going to give us an answer of 2. So my x this time is 1/2. Last but not least, if I rewrite this as an exponential, I have 10 to the x power equals 1 over 100. Well, right now we know that 1 over 100 is 10 to the negative second power, right? Because 10 squared is 100, but we want it as a fraction. So x this time is -2. Now, if you were going to use your calculator to check these answers, okay, how would we type this in? Well, to get the log without a base 10 or a base e, you're going to hit math, alpha, math. And that's going to pop up for you if you have a newer calculator, this lovely little subscript for you to test out. So we can actually test log base 3 of 27, and we get 3. Or again, math, alpha, math. If we test out the second one, log base 4 of 2, we got that 1/2. Or math, alpha, math, log base 10, which officially we could have just used the common log button, of 1 divided by 100 is -2. So our calculator then is verifying for us those answers we got by hand. So again, math, alpha, math, to get that log to type in. All right, now, one last thing, using these log properties then to show about these inverse relationships. Remember, if something is going to be inverses to each other, they are going to allow us to cancel out so that f of g of x and g of f of x equal each other. So if we take f of g of x, so we have our f of x is ln of x, I'm going to plug in for x e to the x. And what I notice is that ln of e cancels out, and I'm just left with x. Well, if we go the opposite way, and I take my g of x, and I plug in for the x value this time, ln of x, again, e to the ln is going to actually cancel out. So this cancels, and again, we're just left with both sides equaling x. So we can see that that these are inverses of each other. All right, and if we check out one more example like that to verify with these properties, again, if I take my f of x value, 1/2 plus ln of x, I'm going to plug in for x, my second part here. So e to the x minus 1/2 power. Well, these cancel, right? And we are left with 1/2 and then plus x minus 1/2, positive minus a negative of the same thing, gave us just the x. And then if we go the opposite way, if I take my g of x, which was e to the x minus 1/2, and I plug in f of x for that x part here, in my exponent, the 1/2 and the negative 1/2 are going to cancel. So I'm just left with ln of x. These cancel. And again, since these both simplified to be x, we know they are inverses of each other. All right, last example for the day on page 64 is asking us to evaluate these kind of using, again, our log properties. So we want to find x if we know that our function log of x equals 7. So again, this is where rewriting as an exponential can really come in handy, because we know if we just have the common log, its base is 10. And if we rewrite this as an exponential, we know 10 to the 7th power equals x. So 10 to the 7th power, we get that 10 billion on that one. And you can also double check, like if I truly took log base 10, or again, that's the common log of 10 to the 7th power, I get 7 as my output value. In the second one, this time we want to find f of x if our x value is 158. So we're going to plug in 158 for our x this time. And the best we're going to be able to do on this is just round. So 2.1987-ish would be your output value. And sometimes that's why logs in the calculator are so useful, is they have things stored that aren't going to necessarily cancel out nice and pretty like this last one did. All right, now we will definitely be working more with logs in class, but definitely something you may want to have jotted down, again, is that idea that we have a log base b of x equals y, that if you rewrote that, its exponential form then is b to the y power equals x. All right, thanks everyone for watching. Work more in class.